Welcome back, class. So today in this video we're going to talk about some other types of intermolecular forces. So last time we talked about dispersion forces and all sorts of things that sort of go along with them and how they get stronger. But a couple of the key points, right, is dispersion forces are present in every single molecule, right? So all molecules have dispersion forces, and the strength of those dispersion forces, we can see a direct correlation to the boiling point. Right? So stronger intermolecular forces are going to lead to higher boiling point. Okay, so what about other types of intermolecular forces? So dipole-dipole is another type that we said will develop in molecules that have a permanent dipole, or in other words, in polar molecules. So in addition, right, and so make sure to note here, right, anytime we talk about these, they're in addition to dispersion forces. So in addition to the dispersion forces, polar molecules, because they have a permanent dipole, can develop these dipole-dipole interactions where the positive end of one end of the dipole is attracted to the negative end of the dipole in an adjacent molecule. And you can see this down here in our sample molecule here, where we have dimethyl ether is what this is called. It's the polar molecule where we get the negative end of the dipole near the oxygen, all the carbon-hydrogen area of the molecule, we get a positive end, and these two can attract us. And you can look at this in a general form. We can look at it with the electron clouds here, where we can see the buildup of electron density here reflected by the reddish color, and the lack of electron density developed by the bluish color here. We can see that attraction. Now, again, how do we think about the strength of these? Well, the size of the dipole, right? So one of the ways that we measured dipole, right, we did it a couple ways. We did difference in electronegativity, we did dipole moment, right? But however we choose to look at it, right, if we look at the size of that dipole, or how polar the molecule is, that's going to play a role in how strong the dipole-dipole interactions can be, right? The stronger that are, the bigger the charges involved, the stronger the attractions will be. And again, this adds on to the dispersion forces. And of course, this means that polar molecules will have higher boiling points than non-polar molecules when we compare molecules of similar size and shape. Now, why do they have to be similar size and shape? Because remember, size and shape are the things that will determine the strength of the dispersion forces, right? So we want to try to compare molecules of similar molar mass and, reasonably similar shape. We don't have to worry so much about the shape because that's a lot harder to look at. But definitely similar molar mass, so that we sort of standardize the dispersion forces. So all we're looking at then is the additional intermolecular forces. All right, so when we have these dipole-dipole forces, let's look at a comparison. So we can look at a non-polar molecule here, ethane, right? So it's one of these hydrocarbon molecules. It has a mass of about 30, right? Looks like this. And we can see that it has a boiling point minus 88 degrees. So this, of course, would be a gas at room temperature. Then we can look at formaldehyde, right? So very similar mass. We look at the structure, right? This is a polar molecule, right? So we're going to have a dipole in this molecule, right? Where the negative part of the dipole is around the oxygen, the positive part around the dipole is around the carbon. And so this molecule, in addition to the dispersion forces, is going to have some dipole-dipole interactions. And here what we see is an increase in the boiling point of about 70-ish degrees, right? So those additional dipole-dipole attractions make it harder to separate the molecules, meaning you have to go to a higher temperature to boil them, to turn them into a gas. Now, granted, these are still pretty low boiling points, right? Below zero, right? And this goes back to really, these are pretty small molecules. Now, I will also point out that we do see a correlation in melting point for these particular molecules, but again, there'll also be examples where we don't see that correlation with melting point. All right, so here we can sort of see, hopefully get the idea of how having these polar molecules, having these additional dipole-dipole, will give us molecules that have higher boiling points. Now, I also said that the size of the dipole plays a role. So we can have multiple polar molecules, right? So there we had a polar and a nonpolar. But what if we have both polar molecules? Then it's the size of the dipole that matters. So we can look at another chart here where we start off just with a nonpolar molecule, propane, kind of like ethane. Okay? And you can see its boiling point. Now, I will point out, notice before you look at the numbers here, notice that these are in Kelvin, right? So this is a gas at room temperature, right? Remember, Kelvin 273 is going to be 0. So, we're going to be, until we get up to here, right, these are all going to be fairly gaseous. They're not going to exist as a liquid yet. But let's look at what we see. So we move over here to dimethyl ether, right? This is a polar molecule, right? This is one of the examples we used a few slides ago as a polar molecule that can have these dipole-dipole. And we see the dipoles going up, right? This is non-polar versus polar. We see the boiling point go up. Now, we move to other polar molecules that have, again, similar mass. So this is ethylene oxide. So it's a bit more polar molecule. We see that the boiling point goes up even a little bit more. We go to another one, acetaldehyde, bigger dipole, more polar. Now we're starting to get boiling points up into where things start to become liquids at room temperature. And finally, you go to acetonitrile, which boils at about 350 Kelvin. So this is going to be a boiling point of 70, 80 degrees, somewhere in there, Celsius. And you can see, right, this is by far the most polar of all of these. So we can see how the size of these dipoles, even among polar molecules, right, is going to have an effect on the boiling point, or an effect of the strength of the intermolecular forces. Okay, so that's dipole-dipole. So let's talk about our next type, which is hydrogen bonds, right? So hydrogen bonding, as I characterized at the beginning, is really just an exceptionally strong type of dipole-dipole. So the basic interaction is the same, which means these are only going to occur in polar molecules as well, but there's an additional criteria here. So it has to be, a polar molecule, but it has to be a polar molecule that has one of these three types of bonds, right? It either has an OH bond, an NH bond, or an FH bond. So we have to have a hydrogen directly attached to one of these three strongly electronegative atoms in order to have this type of hydrogen bonding present in the molecule. Now, why does this happen? Well, if we think about what's going on here, right? If we have a really electronegative atom attached to hydrogen, it means that the electrons are going to be pulled strongly toward that electronegative atom, and it's going to make the hydrogen what we call electron poor. Right? So hydrogen just has the one electron, right? It doesn't have like other core electrons that there, right? So when that electron gets pulled away, hydrogen becomes, basically bare. It has no electrons. It exposes what we call the hydrogen proton, or in essence, we get, hydrogen that develops that positive charge, right? It's, there's lots of words we use for this. We call it deshielded, we call it electron poor, but the bottom line is that exposed proton with that positive partial charge starts attracting electrons from neighboring polar molecules, and this allows for the development of dipole-dipole, but because of the being hydrogen attached to one of these electronegative atoms, that interaction can be extremely strong because of the size or the strength of the positive charge that we see compared to what it might be in other types of polar molecules. And so hydrogen bonds, right, we can characterize them as very strong intermolecular attractive forces. They're strong versions of dipole-dipole forces. So if we're ranking these, right, dispersion forces generally are the weakest. Then we have dipole-dipole. Then we have hydrogen bonding. So as long as we're comparing molecules that have similar mass, we can, have these criteria. And so as a result, molecules that have the ability to hydrogen bond will have higher boiling and melting points than similar materials that can't, right? That can only do dipole-dipole or only do dispersion forces. But again, I will reemphasize again, we can call these as strong as we want to, but they are not nearly as strong as an actual bond. In fact, they are only about 2 to 5% the strength of an actual bond. So while they're strong for intermolecular forces, they're not strong when we compare them to actual bonds. So let's look at an example here. So we have something like HF here, where, so we have our F, we have our H, right? We're going to develop these strong positive charges here on the H, very negative partial charge on the fluorine, right? We can develop these dipole-dipole interactions. So what we can see is it's basically the same type of interaction as we see in a dipole-dipole. It's just there's a bit more strength there because we're dealing with hydrogen attached to these electronegative atoms. And so hydrogen is, again, basically all it has is that positive charge, and it really, really wants those electrons. So it develops these nice, strong interactions. Now, probably most famously is a molecule that exhibits this hydrogen bonding is water, right? Water develops pretty extreme hydrogen bonds, very strong hydrogen bonds. And this is responsible for a lot of the properties of water that we think about, and is a really fundamentally, sort of the fundamental reason why water is the way it is, right? In terms of a lot of its different properties, in terms of its very high boiling point, its very high melting point, for a molecule of its size, right? Remember, water is only 18 grams per mole, right? If you look at its boiling point and its melting point, it should be a gas, right? But it's not a gas, of course. It's a liquid with actually a fairly high boiling point. And that's all due to these hydrogen bonds. So let's look at the effect. So if we go back to our example where we're going to in this case compare dimethyl ether, right? We saw this molecule before. There's about 46 grams per. This is a polar molecule, right? But a polar molecule that cannot hydrogen bond, right? It has no OH, NH or FH bonds, and see it has a boiling point of about minus 22 degrees. So clearly it's still a gas at room temperature. Now if we take ethanol, a very similar molecule, in fact the molecule has exactly the same formula but a different structure, has the ability to hydrogen bond because it has an OH here, right? It has an oxygen directly attached to a hydrogen. As a result, it develops hydrogen bonding, and we can see the change in the boiling point, right? The boiling point goes up about 100 degrees from dimethyl ether, so from negative 22 to positive 78 degrees. So you can see there's a big impact a lot of times when we have these hydrogen bonds present. And if you want to sort of see how this develops, right, we can see that, we have this OH bond, we get this strong dipole developing here, and we can get these hydrogen bonds forming between the different ends of these dipole and adjacent molecules. So, some of the effects of the boiling point with the presence of hydrogen bonding. Now we can look at this sort of on a bigger scheme. We look at the graph on the next slide here. And here we're going to be comparing the molecules of the group 4 elements with hydrogen and the group 6 elements with hydrogen. It's what we call the hydrides of group 4 and group 6. Now, if you look at group 4, right, these are going to be these down here where we have CH4, SiH4, GeH4, SnH4, right? These are, first of all nonpolar molecules. These are all going to be tetrahedral in structure. So they're all going to be nonpolar. They're just going to have dispersion forces. And as we might expect, we see a steady increase in boiling point as the mass goes up. But all well below zero, they boil. Now, polar molecules, such as the hydrides of group 6, right, can develop dipole-dipole interactions, right? So we get, water or oxygen, we get H2S, H2SE, H2TE. These are all going to be polar, right? Think about the geometry. These are all going to have a bent geometry, right? Because the presence of lone pairs. And notice, if we look at 3 of these, right, we see sort of a similar profile. So if we look at molecules that are, in the same period, right, so they have similar mass, right, we can see just, a normal increase in boiling point as you would going from nonpolar to polar, right? Dispersion forces to dipole-dipole interactions. But notice water, right? Water is way outside the trend, right? So if water were following the normal trend, we would expect it to be, down here someplace. But we don't, right? It's way up here. And that is because it can develop these hydrogen bonds, right? These really strong dipole-dipoles that make it unique outside of what we see the normal trends. And if we plotted this for, say, group 5 elements, right, we would notice the same thing for ammonia, right? We would see ammonia, we would see the other group 5 elements and their hydrides have sort of a normal pattern with dipole-dipole interactions, but then ammonia would abruptly go up because of its ability to hydrogen bond. All right, so hopefully we can see some of the dramatic impacts that we can have when hydrogen bonding is possible. Now, there is one last type of intermolecular force that I want to speak about, and these are what are called ion dipole forces. And these are present in a very specific example that I want to talk about. And these are the forces present when an ionic solid is dissolved in a polar liquid. Now, these are what we refer to as aqueous solutions of ionic compounds, right? So when we take sodium chloride, dissolve it in water, or some other ionic compound in water, one of the ways that we explain why these are so stable and why these materials dissolve so easily is the presence of these ion dipole forces. And so what are these? Well, basically what we see is that when the ionic compound dissolves, right, it separates into its ions. And when we have water, or to some extent other polar solvents as well, but we're going to focus on water, we have the ability of the dipole in these polar molecules to be attracted to the oppositely charged ion. So we see the chloride ion here is attracted to the positive end of the dipole, and not only just to one water, to a bunch of different waters. So we develop what's sometimes called a water cage or a solvent cage, where these ions are surrounded by water molecules either interacting with the positive end of the dipole for the negative ion, or interacting with the negative end of the dipole for the positive ion. And we have the formation of these ion dipole interactions, right? So these are the ion dipole interactions, and these are quite strong, right? These are, on par stronger than a hydrogen bond if we're sort of standardizing them. And so the fact that these ions can develop multiples of these, like 6 or so is sort of the standard number, around each ion, makes these ions quite stable in solution, makes it harder for them to want to get back together with each other and, reprecipitate, if you will. And so these ionic compounds, for the most part, form very stable, easily dissolvable in polar liquids like water, right? And so ion dipole forces are a special kind of intermolecular force that we see in aqueous solutions of ionic compounds. And we use these to account for the ease and of solubility of these ionic compounds in water. So let's summarize here. So first of all, dispersion forces. These are the weakest of all the intermolecular forces. They're present in, of course, all molecules. And the magnitude of dispersion forces increases with molar mass, right? So molar mass is sort of the biggest factor. We also looked at shape, but the magnitude of these increases with molar mass. Now, so all molecules have this base dispersion force. Now, if you have non-polar molecules, right, this is something that if I haven't emphasized, I will. Of course, non-polar, this is only have dispersion forces. Now, when we move to polar molecules, we now have the ability to have additional dipole-dipole attractive forces because of the permanent dipole. And so we see, when we compare molecules of similar size, we see polar molecules will have higher boiling points than nonpolar molecules. Now, certain other polar molecules, ones with OH, NH, and FH bonds, can develop hydrogen bonds, right? And these are the strongest of all the intermolecular forces that a pure substance can have. They will be present when we have hydrogens bonded to O, N, and F, or N or F. Now, the most common of these are, of course, OH and NH, because there's only one molecule that has an HF, and that's HF, hydrofluoric acid. Hydrogen bonds are also sort of specially considered, or they have this special place because they're really important in a lot of biological molecules. DNA, for example, the two strands of the DNA molecule, and there's a picture in the book, or you may discuss this in biology class, right, are held together by hydrogen bonds. So this accounts for the stability of DNA, right, because these are pretty strong, holds the two chains together, but not so strong that they can't be separated when they need to be for, to unzip the double helix. And then finally, we looked at ion dipole attractions, which are present in mixtures of ionic compounds in polar molecules. The most important example of this being aqueous solutions of ionic compounds. And these are going to be the strongest of all the intermolecular attractions. So we'll just close this little section with the little graphic that's in your book, which kind of gives a nice, sort of easy to look at comparison here, where we can look at the types of molecules that they're present in, there are mixtures for ion dipole, and we can compare sort of the relative strengths. So you can see, that, you got to be careful of the ranges here, because you can see dispersion forces can get quite strong in very large molecules, right? So you got to be really careful about comparing, a large nonpolar molecule to a small polar molecule, and just automatically saying the polar molecule is going to have a higher boiling point or whatever, because, these things can overlap if we compare different sizes of molecules. That's why we try to be careful about only comparing molecules of similar size, things like boiling points. Now, the other thing that I will point out here is look at even the strongest of these, right? For hydrogen bonds, up to about 40 kilojoules per mole. Ion dipole, maybe higher, up to 100. Sort of a bond, a covalent bond is going to be, on average, let's say anywhere from 250 to, 800, up to, if you get triple bond stuff, but, it's going to be 250, 300, 400 kilojoules per mole. So, many times stronger than even the strongest hydrogen bonds that we can see. All right, so that brings to conclusion our discussion of intermolecular forces here. We will continue on in the next section, talking about phase changes, focusing on vaporization, and then later on talking about some of the other phase changes, melting, sublimation, etc.